So welcome to session number 2 of module 1 of the subject mechanics of materials. So in session 1 of this module you have just understood some important basic concepts of mechanics, and also we have seen different materials available for engineering applications. So in this session we will continue with the concept of stress and strain, and before we define what is stress and strain, let us look at different kinds of loads applied on the engineering components or structures. So usually in engineering we take the object or the material and it will be given some shape and size to take the load. So we name them according to their applications or how they are used. For example, in this diagram or in this drawing we have a material, a length of the metal is there, and if you look at the cross section, it can be any cross section. It can be circular cross section or it can be triangular or rectangular, whatever it is. Just to assume one column. For example, this is a column and the base is fixed permanently here and the other end is free. So if you just assume this as a column, in the front view you can see only the length of this, but cross section is not seen. So you can assume that the cross section can be square or circle, whatever it is. So here, to understand what are the types of loading or how the load is applied on the structures or mechanical members or structures, we can say them as the first kind of loading or the common loading is the axial loading or the axial load. So you can apply the load or force on the mechanical structures or civil structures. For example, this column in such a way that the load is applied along the axis of the member or the column here. So you take any object or any component, it will be having what is called as the axis line or the axis. So axis is the line, imaginary line which divides the object or the material into symmetry. So here when you apply the load exactly or along the axis of the body or the component or the part or mechanical structure or any structure, that load is called as axial load. So whenever you apply the load along the axis of the material, that is called as axial load. Similarly, you have transverse load. So here the load is applied perpendicular to the axis of the material or the component or the structure. So you can use the word structure or member or something like that, because they are the part of the mechanical system or maybe civil system, civil engineering system. So in this case you have a component or a member, structural member, which is vertical along the length here, and depending on how the load is applied, in which direction the load is applied, we have axial load and the transverse load. So axial load is nothing but the load is applied along the axis of the component or the structure or the member, and this one more kind of load is called as transverse load, where the load is applied perpendicular to the axis of the member or the component. So similarly, you have one more member here, structural member, and in civil engineering language we call this as beam. Even in mechanical structures also we use this kind of members here. So this is called as a beam. So this is called as a column and this is called as a beam. So here you can see the beam is usually horizontal and it is supported on the columns here. The columns will be below the beams. So when the load is applied axially, I told you it is axial load. When the load is applied perpendicular to the axis of the component, it is called as transverse load. So the same thing applies to this member also. So whereas this structure is vertical, column is vertical, and this structure is horizontal. So whatever may be the configuration of the structure or member, basically in what direction or how the load is applied. So based on that direction, we call them as axial load or transverse load. So again, in this case, when the load is applied along the axis of the beam or the structure, it is called as the axial load. Similarly, when you apply the load perpendicular to the axis of the structure or member, it is called as transverse load. Just remember, this is the basic loading, axial load and transverse loading on the structure or any component. So similarly, here the axial load is again, you can apply, you are applying along the axis, but the direction can be in any, maybe upward or downwards. So depending on the directions of the axial load, you can say that axial load can be tensile load or compressive load, or tension or compression. So when you apply the load, axial load on the member, so this is the component. So just imagine a column. This column is here in 3 dimension. So we have the cross-sectional area here, and this is the length of the particular member. And on the 2 ends, I am applying a load in opposite directions. That means I am trying to pull the component. So that is called as the tensile axial load, or simply tensile force or tensile load. And when you apply tensile load on the material, on the component, so we say that the material or the component is under tension. So we use the word tension, and the force is called as tensile force. So this is a tensile force. So tensile force is an axial force, remember that. And similarly, when you apply the force in such a way that it's axial load and the load is acting towards the material, towards the structure, towards the member, that means you are trying to compress that particular component or the bar or the material. So it is axial load and it is acting towards the material. That load or force is called as compressive force, and we say that the material is under compression. So compress, the word, compress, all of you use the word compress. So compress means to push the material inside that only, or to apply the load inside the material, towards the material. So that causes compression of the material. So remember that tensile force and compressive force, they are the axial forces only, because they are acting along the axis of the component, and tensile force is acting away from the component, and compressive force is acting towards the component. And we have one more concept here, one more kind of loading called a shear loading. So shear loading is a transverse load. You can see here, this is the component, vertical component, vertical object, or a bar. We call it as a bar, square bar. It is square here, cross section is square, and its length is there. So we can call this a square bar or square, something like that, member. So here the load, you can see the force is applied perpendicular to the axis of the particular bar. So this load is called as transverse load. So when this transverse load is applied at the 2 ends, so it causes the shearing, or what is called as cutting of the material. So it is called as shearing or shear force. So this kind of force is called as shear force. It causes the cutting of the component. The material will get cut here because of this shear force. That's why it's called as shearing. Shearing means cutting perpendicular to the axis of the material. And we have one more understanding of how the load is applied. So all of you know about the word bending, bend. So whenever you take a long structure or long member material, rod or shaft or a bar, and you try to bend it, so you are applying force at these 2 ends. So this is a transverse load here, because you are applying load perpendicular to the axis of the component, and to bend it, one more reactional force will be applied here. So what happens, because of this nature of transverse load, the material will bend. That is called as bending. So material is under bending. So all of you know this. You take a stick or you take a steel bar and you try to bend it. So you are applying the force at the end, and that force is transverse load. And at the middle also you are applying a transverse load that causes bending of that bar or the member or the object. Similarly, we have one more kind of loading called as torsional loading. So torsion means you are applying a rotational moment. So you are trying to rotate the object or the material. So you take a round bar, cylindrical bar, and you try to rotate it. So that is called as twisting or torque or a twisting moment. So you are trying to twist it. So when you apply the load in angular manner, in angular direction, it is called as twisting, or we can call it as torsion. And that force is called as torsional force or a twisting force or a twisting moment here. And we say that the material is under torsion. So twisting is nothing but torsion. So these are some of the ways, different types of forces on which are applied on the different machine components or any structures which are made up of different materials. So coming to the first concept, stress. So the word stress, what does it mean actually? So here you have a member here, a bar of particular length, and imagine some cross section, maybe it is a circular rod. Imagine a circular rod, and on that circular rod you are applying a load, tensile load. So this is a circular rod and you are applying a tensile load P. So P is a force, it's axial force, and also it is depending on the direction of the force, I can call it as a tensile force because it is acting away from the object. So when you apply the load here on one end, at the other end it is fixed, so there will be reaction force in the opposite direction. So this causes the steel rod or the material or that particular structure to elongate. So this, when you apply the load on the material, so this load will be distributed, will be transferred inside the material. You can see, okay. So if we take the cross section of the material, you take the cross section of the material along XX. So at XX, you can see when you apply the load P, there will be reactional force acting in the material. That means the material will react or it will try to resist the load applied. So this is a load applied, and inside the material, because of its strength, the property strength, the material will resist that particular load what we are applying over this area. So this is a cross-sectional area. You just cut the material along the axis, perpendicular to the axis, that is called as cross-sectional area. So whatever load you apply on the material, that material it will develop resistance to the force over this area, cross-sectional area. For example, if you take yourself, for example, you are studying, and studying is nothing but just like a force on you. So I'll tell you that you have to study for 1 hour or 2 hours or 3 hours, something like that. That means I'm increasing the load on you. So that P, the load or force on you, I'm increasing. That means if I ask you to study for 1 hour, you will study. If you start learning or studying, if I ask you to study for 2 hours, somehow you will manage to study. But if I ask you to study for 3 hours continuously, you cannot handle that particular force or the external factor studying. So what you study, you resist, you oppose that studying for more 3 hours or 4 hours depending on time. So here similarly the material also, as you go on increasing the load force, okay, or when you apply the load on the material, it goes on resisting or opposing that force depending on the strength of that. So as in your case, if I ask you study for 1 hour, 2 hours, you study, because the capacity of you yourself, the strength of yourself is 2 hours studying capacity. But if the capacity, if I increase that to 3 hours, you cannot study. So you can resist, or you can hold, you have the capacity to study for 2 hours. The studying is nothing but the external force which is applied on you. So similarly on the material, when I apply load P, some load P, it will start resisting over the area. So this cross-sectional area is important here. So what the load you apply in the material, so that load, the ratio of that load divided by that area, we simply call it as stress. So mathematically, stress is nothing but load by area. So the stress is a phenomenon. It is characterized, is given as by symbol sigma here. So it's a normal stress. So the load is applied normal to the cross-sectional area of the material. So this load is applied normal to the cross-section of the material. And whenever you apply load on the material start resisting that load. It will start opposing that load. So that resistance offered by the material over the cross-sectional area to the load applied, that is called as stress. Okay, so we can define stress as the resistance of the material offered by the material over the area, cross-sectional area. It resists what? It resists the load. So resistance applied, resistance offered, or resistance in the material to the applied load over the cross-sectional area, that is called as stress. So mathematically it is stress is equal to load by area. So load is P here, and area is A is the cross-sectional area. So in symbols we use sigma for stress. For load we can use capital P or F depending on the different authors. And the sectional area is capital A is the cross-sectional area of this member or structure. So the cross-sectional area can be circular, or it can be rectangle, square, whatever it is. Okay, so mathematically stress is nothing but load by area. And if you want to define stress, we can define stress as resistance offered by the material to the applied load per unit area or per cross-sectional area, that is called as stress. So for any phenomena or any physical quantity, we have the units. For example, load, the unit of load is Newton or kg. So this is kg or Newton. So usually in SI units we take load in newtons. And what is the unit of area? The unit of area will be millimeter square or meter square, whatever it is. So when I put, for example, say when I take P as 10 Newton, P is 10 Newton, and cross-sectional area is 5 meter square. So these are all the values. So you put the value of load and value of area in terms of units. So if I take load as 10 Newton, area is 5 meter square. So what will happen? 10 by 5 is 2. So 2 Newton per meter square we will get. So that Newton per meter square or Newton per millimeter square, it is the unit of stress. So Newton per meter square is the unit of stress. And 1 Newton per meter square is called as Pascal. So Pascal is the unit of stress. So we'll express the stress in terms of Pascal here. So stress is Pascal. So for example, if I ask you what is your result, examination result, you will tell 60% or 75% or 80%. Like that, if I ask you what is the stress of this material, stress induced in this material because of this load, you will say it is 2 Newton per meter square or 2 Pascal. And usually the materials, the strength of the materials will be expressed in megapascal. So mega is nothing but 10 to the power of 6. So it is 200 megapascal or 300 megapascal, something like that. So some materials, different materials, they have different stress or strength depending on their properties. So usually the stress is expressed in Pascal or megapascal. So remember, Pascal is Newton per meter square. Depending on the value, how much quantity is there, 10 power of 6, or I can put kilo also here. So kilo means 10 power of 3. So kilopascal or megapascal or gigapascal, something like that, depending on the value of that number on the stress. So usually, and also you can express area in millimeters also. So millimeter or meter is nothing but the unit of distance. So you can express in area in millimeter square or meter square. But in SI units, if I express area in meter square and load in newtons, so that is the unit of stress. Newton per meter square or Pascal is the unit of stress. So anyway, we will understand this when we solve some problems later. So here, so in this case, the stress can be tensile stress when you apply tensile load here. Similarly, if I take this object and if I apply compressive load, that is the load in the opposite direction towards the material, the stress is called as compressive stress. So stress can be tensile when the load is tensile load. Stress can be compressive when the load is compressive force. So here you can see the stress here, and this is particularly tensile stress. So we have taken an object, a material is there, a structure is there, and this is the cross section of that material. It's a square cross section. You can see it is shaded there with a blue color. So this is the cross section of the material. So this is the cross sectional area of that material. You can calculate the area depending on the geometry of this cross section. So here it is a square. So area of square, you know, it is side by side. Okay, so edge by edge, like that. And you are applying the force Ft. So F is the force, T is for tensile. So this load or force is tensile force. This load or force is tensile force. F is for force or the load, T is for tensile force. So when I apply load Ft over the area, how I can calculate stress? So stress is sigma here. So stress is nothing but tensile load divided by the cross sectional area A or A naught, whatever it is. So the load is Ft here, tensile force. Area is A only, or you can take A naught, whatever it is. So the stress sigma will be load by area. Okay. So the load or the force is in newtons and area is in meter square. So the unit of stress is expressed in Newton per meter square. So since this is the tensile force, I can call this as tensile stress. Similarly, I have what is called as shear force. So on this, and one more thing you have to remember here is that tensile force is acting perpendicular to the surface area of the material. So this is the cross sectional area or the surface area, and the load, tensile load, will be acting perpendicular to this surface or cross section. But we have a load which is acting parallel to the surface, or which is acting on the surface in this direction or in this direction or any direction. So when the load is acting on the surface, along the surface or parallel to the surface, that load is called as shear load or shear force. So Fs is called as shear force. So here you can see this is the surface or the cross section or the area of this cube of this material. So on this surface, when I apply load perpendicular to this surface, perpendicular to this face, I call this as tensile force. When I apply load parallel to the surface, on this surface, that is called as the shear force, Fs. So the stress when you apply the shear load is called as shear stress. When you apply tensile force, that stress is called as tensile stress. It is sigma. Shear stress, I am using the symbol tau here. Okay, just look at the diagram, you can understand. So you should understand the difference between tensile load and the shear load. So for tensile load, I am having a tensile stress sigma. For shear load or shear force, I am having shear stress tau. So any stress, any load, any force, any type of stress or load, any type of force or load will be having corresponding stress. If the load is tensile, the stress will be tensile stress. If the load is shear force, then the stress will be shear stress. So tensile stress is sigma, shear stress is tau. Similarly, if instead of applying tensile stress, tensile load, I can apply compressive load. You can see here, this is a cube, a material is there, and I am applying compressive load. And in this diagram, the load applied is tensile load. So this is tensile load, and when you apply tensile load over this area, if you divide this load by area, you will get tensile stress. And when you apply more and more stress beyond the strength of the material will fail. The material will fail. So it's a common thing. So if you apply load or force beyond the capacity of the material will fail. That is there. The failure is there. It depends on how much load or force you are applying. But if you want to know the stress in the material, how much stress is there in the material, you simply divide the force by the area. So if the load is tensile load, tensile force, the stress will be tensile stress, sigma. Similarly, on this material I am applying compressive load. So the direction of the load is towards the material. So it's a compressive load. So when the load is compressive, then what will be the stress? Stress also will be compressive stress. We call it as compressive stress. The formula remains same. Compressive stress is equal to compressive force by area. Tensile stress is equal to tensile force by area. Similarly, shear stress tau is equal to shear force by area. So the basic formula for stress remains same, force by area or load by area. So it depends on what kind of load you are applying. If you apply tensile load, you will get tensile stress. If you apply compressive load or compressive force, you will get compressive stress. If you apply shear load, you will get shear stress tau here. And shear load, you can see how it is applied. The shear force is applied parallel to the surface. So on this upper surface, it is in this direction. So to maintain equilibrium, there will be another force, shear force, opposite to this force. So if this force is acting in the right hand side, on the below surface, bottom surface, this force will be acting in the opposite direction. So this causes the material to fracture in this way. It will cut, the material will cut, it will shear into two pieces when you apply shear load. But when you apply tensile load and compressive load, you can see the cracks will be there, and cracks will open in different manner, in different directions. But in shear load, when you apply the shear load, you can see on this surface the shear load is applied in this direction. On this surface, the shear is applied on the other direction. So this shear force which is applied on the material, one direction and other direction. So what happens? The material will get cut in the center here, in the middle of the material. So this is called as shearing. And the stress in the material is called as shear stress. So the formula is shear force by shear area. So for all stresses, the formula remains same. So we have the normal stress. So the tensile stress and compressive stress are called as normal stress because the load is acting normal or perpendicular to the face here, face of the material. That's why it is called as normal stress. So tensile stress and compressive stress, they are called as normal stress also. Normal stresses. So normal means the load or the stress is acting perpendicular to the cross-sectional area. Shear stress is acting parallel to the cross-sectional area. It is acting along the surface or along the cross-section of the material. That's why it's called as shear stress. So we have normal stress and the shear stress. And in normal stress we have tensile stress and compressive stress. And in shear stress we have only the shear stresses here, where the stress will be acting in a transverse direction. So shear stress is transverse direction, whereas the normal stresses, tensile and compressive stresses, they are axial stresses. They are acting along the axis of the material. So if you go back, so the normal stresses, tensile stress, compressive stresses, they are called as normal stresses. So normal stresses are also called as axial stresses because the load is acting axially. Whereas shear stress is because of the shear load, which is also called as transverse load. So in shear stress or shear load, it will be acting perpendicular to the face or to the perpendicular to the axis. So that's why it's called as shear load or transverse load. So the shear stress is shear load or transverse load divided by area. Tensile stress or compressive stress is because of the tensile force or compressive force. But the formula remains same. Stress is force by area. Stress is force by area. So the force or load where it is applied, on which area it is applied, that ratio is called as stress. And the formula remains same for all the stresses, force by area, and the unit is Newton per meter square. The force is Newton, area is meter square. So the unit of stress will be Newton per meter square. And here also you can see the load is applied, tensile load is applied on the material, on the bar at cross section NN. If you take the cross section here, so here the load is applied, tensile load is applied, and this is the internal resistance or the reactional force inside the material. So when you apply external force F, the material also will react internally. Inside it will resist, or it will show resistance to the applied force. So internally also load will be, stresses, forces will be inside the material. It will start in the opposite direction. So this external load is opposed by the forces in the material, developed in the material, or the resistance. That force is called as resisting force. It's again the force only. So this force by area, over the area, it is called as stress. But usually over the area at the edges the stress will be less, or the reaction force will be less, and in the center it will be more. But usually we take that force as the average force, or the stress, it will be average. So coming to strain, so we understood stress. So stress is related to the load acting on the material over the cross-sectional area. Then what is strain? So strain is related to the deformation or change in shape and size of the material. So stress is related to the force acting on the material, over the area, whereas strain is related to the change in shape of the material when you apply the load. So whenever there is a load applied, there will be two things happening in the material. So one is the stress, other one is the strain. Okay, so strain is related to the change in shape and size of the material when load is applied. So mathematically, I can say that strain is nothing but change in length by the original length. So since I am taking axial load here, or linear load, this is strain is called as linear strain or axial strain. So the strain which is acting because of this axial load. It is called as axial strain, and it is also called as normal strain because the load is acting normal to the cross section of the object or perpendicular to the axis of the object. So it's also called as normal strain, normal stress, normal strain. So we have the symbol for strain is eta here. So just like the symbol we use for stress sigma, for strain also we use the symbol eta here. Sorry, epsilon. So epsilon is equal to change in length by original length. So mathematically strain is calculated by this formula, change in length by original length. So the original length of the material is, this is the initial, before applying the load, this is the material or the component. So it's a circular rod. So this is a circular rod of length L. So the initial length of this rod is L. So this is the original length. And once you apply the load, so this is the load applied. So the load applied can be of any magnitude, 10 Newton, 20 Newton, 30 Newton, 40 Newton, like that. So once you apply the load, depending on the quantity of the load, amount of load, the rod, this rod, circular rod will extend. So that extension of the rod, the shape and size of the rod after extending, it is shown with the dashed line here. So this is the original shape and size of the circular rod or bar before applying the load. So once you apply the load, the length of the rod will increase. The length of the rod will increase. Length of this bar will increase. So initially the length of the bar was L, and when you applied the load, the length increased by so much of amount, delta L. So this is the change in length when you apply the load here. So mathematically the ratio of change in length, that is delta L by the original length, it is called as strain. Okay, so just remember, and one more thing in strain is the units of strain. So if you take the length in millimeter or meter, and if you take the change in length also will be in meter or millimeter, you can take meter only. So if the original length is L meter and change in length is also in meter, it will get cancelled. So basically the units of strain will be, it will not be there, or you can simply take it as meter by meter. So you can say that strain is unitless in simple words. So you can say it has no units, or the strain is unitless. Whereas in stress, the units is Newton per meter square, because of the force Newton and area meter square is Newton per meter square. Here also the strain is having units, but since the units are same, meter by meter or millimeter by millimeter, we say that it is unitless. Or if you want, you can say millimeter by millimeter or meter by meter. So basically strain is change in length by original length when you apply the axial load. So okay, you can ask that the material, this is the diameter of the rod here, circular rod. When length increases, diameter should decrease because the volume has to be maintained. So you can ask, you will observe that when you apply load axially, the length increases and also the diameter also decreases. So the strain will be there along the diameter of the rod also. So that we will discuss later. So this strain, you remember, it is in the axial direction. So this strain is in the axial direction. So I am taking only the length here. I am not considering the diameter of the material. I am not taking the lateral dimensions here. I am taking only the linear dimensions along the axis. So just like normal stress, we have normal strain because the load is acting perpendicular to the area. So we have normal stress and we have normal strain. So normal strain is change in length by original length. So we are taking strain with respect to length only. We are not discussing about diameter. That we will see later. So this is the concept of strain. So just remember, when you apply load on the material, any load P or force on the material, two things will happen. So one is the stress will be induced or developed in the material, and that stress is load by area mathematically. At the same time, when you apply load on the material, there will be strain in the material. So strain means change in shape and size. So what is changing here? Here the length is changing. So the ratio of change in length by the original length is called as strain. Okay, so if you take the strain, if you want to calculate strain, if you take this as delta L by L, and if you multiply by 100, it will give in percentage. So I will tell that strain is 5% or 6%, something like that. So it depends on the material. The strain depends on the material. So material which are strong, which are having high strength, the strain will be less. And the materials which are strength is less, strain will be more. For example, you take steel. Steel, the strain will be less compared to the strain in elastic materials or plastic materials, like that. And similarly, if you compare strain with concrete or RCC with the mild steel, so mild steel will be having more strain compared to the concrete material, like that. Okay. So here we have elastic limit. So you should understand what is this. And here also we have what is called as Hooke's law. So once we have studied stress and strain, so we look at what is elastic limit. So here, once we apply the load on the material, so depending on the capacity, I told you depending on the strength of the material, it will resist the applied load. For example, say I am applying 10 kilonewton here, 10 Newton here, it will elongate. Okay, when I apply the load 10 Newton, it will slightly elongate this much. When I apply 20 Newton, it will elongate by this much. When I apply 100 Newton, it will elongate by this much. So as you go on increasing the load, the elongation of the material goes on increasing. And also the stress in the material increases when you go on increasing the load here. So when the force increases to 10 Newton, 20 Newton, 100 Newton, the stress also goes on increasing. So simultaneously, when you apply load on the material, stress and strain will be observed in the material, and that causes excuse me. So whenever you apply load on the material, it causes stress and strain in the material, and that strain, you can see that's elongation of the material will be there when you go on increasing the load. So it depends on the load here. So initially, when you apply load on the material, that length increases. So as you go on increasing the load more and more, higher loads, what happens is that the material will elongate permanently. So initially the elongation is elastic. We say that at lower loads the strain or elongation will be elastic in nature. That means, suppose say I apply 10 Newton here and elongation is delta L, and when I remove this 10 Newton, when I remove the load back, the material will come back to the original length. That is called as elastic deformation or elasticity. So we studied about elasticity in the mechanical properties in the previous session. We discussed about elasticity. So what is elasticity? Elasticity is nothing but when the load is removed, the material or the bar or this rod will come back to the original length. That is called as elasticity or elastic deformation or elastic strain. So strain or elasticity is related to the change in length of the material. Okay, so just remember that elasticity is related to the elongation of the or change in shape of the material. So once we remove the material load applied, so once the load is applied, stress and strain will be there. Once the load is removed, strain will again come back to zero. That means the material will come back to the original length. That is called as elastic deformation. But as you increase the load more and more, okay, so that resistance offered by the material will be, it also goes on increasing. And what happens is that when you apply the load beyond the resistance or beyond the capacity of the material no longer resists that load, it cannot hold that load, and it will deform plastically. So that is called as plasticity or plastic deformation. So until some amount of load, depending on the material will elongate elastically, or what is called as elastic deformation. Once the load reaches the maximum capacity of the material will elongate, okay, it will deform plastically, or what is called as plastic deformation. So that's what in this slide here we have called as elastic limit. So we are using the word limit here. So limit means all the materials will have certain limit for the load. So below that limit of the load, it will show elastic deformation. Above that particular load, it will show plastic deformation. So that particular point limit of the load is called as elastic limit. So below that elastic limit, the metal will deform elastically. That means when you remove that load, it will come back to the original length. So that limit of the load is called as elastic limit. So elastic limit is nothing but that load where the material shows elasticity, or the material deforms elastically. That means after that, when you remove that load, it will come back to the original length. That is called as elastic limit. So in the elastic limit, so all the materials will have elastic deformation for some amount of load. So when the load increases more than that elastic limit, then the metal undergoes plastic deformation, permanent deformation, or permanent elongation, depending on the load, tensile or compressive. So here, just remember, here we have to understand on concept Hooke's law. So Hooke's law is based on stress and strain. Okay, so in the elastic limit, or when you apply the load to the material within the elastic limit of the material, so what happens? There will be stress and strain in the material. So whenever the load is applied, I told you there will be stress and strain in the material. So below that particular load, or within the elastic deformation of the material, or when the load is below the elastic limit of the material, the stress will be proportional to the strain directly. So that's important here. So within the elastic loading, or within the elastic limit of the material, if you apply the load, then the stress induced in the material will be directly proportional to the strain in the material. So just now we saw what is stress and what is strain. So whenever you apply load on the material, there will be stress and strain in the material. Okay. So again, if the load is within the elastic limit of the material, then we can apply the Hooke's law. So what is Hooke's law? Hooke's law states that stress is proportional to the strain within the elastic limit. So this is important. So within elastic deformation, or when the load is below the elastic strength of that material, elastic limit of the material, then the stress is directly proportional to strain. So we'll study this in detail later, in detailed concepts later. So just remember here, mathematically, stress is proportional to strain in the elastic limit. That is what is the Hooke's law. So Hooke is again the name of the physicist or engineer who has studied this and given this statement. Okay, so this stress can be this can be tensile stress or compressive stress, whatever it is. Okay, it is a normal stress here. The stress is proportional to strain. So if I remove the proportionality constant, okay, what will happen? I will get one proportionality constant here called as modulus of elasticity, or Young's modulus. So stress is proportional to strain. I am just removing that concept here. So stress by strain will be equal to proportionality constant. That constant is nothing but it is called as Young's modulus, or it is called as modulus of elasticity, because it shows how much elastic the material is. And this modulus of elasticity is also called as, it's a measure of stiffness of the material. The stiffness, again, a property we studied in the previous session. What is stiffness? So stiffness, Young's modulus or modulus of elasticity, it will measure the stiffness of the material. That means how rigid the material is. Okay, so that is the Young's modulus. So this constant of this proportionality constant, sigma by E, stress by strain, is called as the modulus of elasticity or Young's modulus. So here Hooke is, again I told you the name of the person or engineer who has given this relationship, and one more engineer called as Young, his name is Young, I don't know his full name, part name is Young here. So he proposed this, he extended this statement, Hooke's statement, he extended it and gave this, he calculated this modulus of elasticity, and that's why it is called as Young's modulus. It's a name here, name of the engineer. So he proposed this constant of proportionality, and that is called as modulus of elasticity. Right? So here elasticity is, Young's modulus is equal to stress by strain, and this is obtained by this one here, stress is proportional to strain, or stress by strain is equal to constant, and that constant is the Young's modulus or modulus of elasticity, and that is given by capital letter E. So when I put the formula for stress and strain here, so what is the formula for stress? It is sigma here. So sigma is P by A, force by area. So what is the formula for strain? Change in length by the original length. So if you rearrange the term, it will become PL by A delta L. So when I put the dimensions or units for this P and L, all those things, so this and again you will get the units Newton per meter square. So the unit of Young's modulus or the unit of modulus of elasticity is Newton per meter square or Pascal. So an example is given here. So different materials, they have different Young's modulus or different modulus of elasticity depending on their properties, mechanical properties. So one such metal is steel here. So for steel it has been tested and calculated that Young's modulus is around 200 gigapascal or 22 lakh megapascal. So mega is 10 power of 6 and 10 power of 9 is gigapascal GPa. So it is 200 GPa. So Young's modulus for steel will be around 200 GPa. So this is particularly for mild steel. So again in steel we have varieties of steel depending on the alloying element. So this is simply for mild steel. So it is around 200 gigapascal, or we call it as GPa. So Pascal is Newton per meter square, and M and G, they are the values 10 power of 6, 10 power of 9, something like that. So just remember this concept here. So this is about the properties. So this is Young's modulus is called as one of the property of the material. It's a mechanical property, and it's also called as elastic property of the material. So property means it is a characteristic of materials. So different materials, they have different properties. Okay, so all the materials will not have same values. So all the materials, they have Young's modulus or modulus of elasticity, but the values will be different for different materials. That you have to keep in mind. So just remember different loads here, different stresses depending on the loads, and how to calculate the strain, and what is Hooke's law. So Hooke's law relates stress and strain in the elastic limit. So different metals, they have different values of elastic limits or Young's modulus, and this E is the property, one of the property of the materials. It's a mechanical property of the materials, and particularly it is called as elastic property of the material. because it is applied in the elastic region or elastic deformation of the material. So we'll stop with in this session. This session will stop here, and further concepts we'll look at in the next sessions. Thank you.